All right, resuming on from yesterday's discussion. Now, when we left off yesterday, I posited the question, could we have just used the original triangle ABC's perimeter and area to help us figure out what the perimeter and area would be for the dilated shape? And I said the answer to that was yes and yes-ish. So here's what we're going to do. All right, so let me kind of clear off some area here. So I'm going to keep my original perimeter and area so that we know what to kind of compare things to here. Oh my goodness, that really got jacked up. Whew. All right, I guess let me just erase this and I'll just rewrite the area up here. All right, so we knew the area of triangle A prime, B prime, C prime. That was equal to 112 and a half. Okay. All right, so now let me kind of erase some room around original triangle ABC. And let's figure out, let's do perimeter first. That was the one that took a little bit longer to do. But again, hey, you know what? This side right here, AC, we can still count that. That had a length of 5. Okay. What about, what do we do next? We went over here to AB, right? So let's do that. Let's do how long is segment AB so we can get that side of the triangle. Well, let's see. This is 1, 2, 3, 4. Okay. And this has a length of 1, 2, 3, 4, 5. Okay. So Pythagorean theorem. Tell you what, I'll do my Pythagorean theorems over here. So 4 squared plus 5 squared equals c squared. 16 and 25 add up to be, what, 41 equals c squared. And then we'll take the square root of that. And the square root of 41 is prime. So the length of segment AB is exactly the square root of 41. It doesn't simplify at all. All right? So now let's go down here. We got one more side to figure out. Side BC. We got this really little skinny right triangle down in here, right? So let's see. This has just got, it's a length of 1, and then 1, 2, 3, 4, 5. So this right triangle that's right here, barely squeezing in. So yeah, let me clear off this so I can do some Pythagorean theorem. What do we got? 1 squared plus 5 squared equals c squared. 1 plus 25 adds up to be 26 equals c squared. Square root both sides. And now 26 isn't a prime number, but even if I break it down into the square root of 2 and the square root of 13, then 2 and 13 are both prime, and I don't have any repeated factors. So really, in the end, the square root of 26 is fully simplified. So the length of side BC, or segment BC, is the square root of 26. All right, so there, I got my 3 sides now. So the perimeter of triangle, original triangle ABC, is the square root of 41 plus the square root of 26 plus 5. Now, how does that compare to the dilated perimeter that we got previously? And some of you are maybe starting to see it. Is this perimeter, the dilated perimeter, is it 3 times larger? And some of you are hopefully looking at the little individual parts there. Hey, look, here's a 3 root 41. Here's a 1 root 41. How many times bigger is 3 root 41 compared to 1 root 41? 3 times bigger. Do you also see it here? 3 root 26 is 3 times bigger than the square root of 26. And last but not certainly least, 15 is 3 times bigger than 5. So yes, we could have originally just taken our original perimeter and multiplied each side by 3, just like what we did previously with challenge day problem number 2. We could have multiplied each side by 3, and yes, we could have gotten the new perimeter. Now, the interesting part, the area. So let me clear this off. And we're going to do the area really the same way that we did the area before. We're still going to use this side because it's perfectly vertical. We'll call that the base. And the height's going to start at B, and it's going to fall perpendicularly to this vertical base, and this height is also 5 if I count it out there. All right, so the area of triangle ABC is going to be 1/2 base times height. So 1/2, 5 times 5 is 12.5. Okay, so obviously now, if I had just taken my original area and multiplied it by 3, 12.5 times 3 is no way going to give me 112.5. Guys, this is weird. What's going on? Huh? Oh, this must be the one that doesn't work, right? But it does. Now, let's explore this. If 112.5 is not 3 times bigger than 12.5, how many times bigger is 112? No, not 1012. Come on. 112.5, divide it by the original 12.5 area. How many times bigger is that? It's 9 times bigger. That's weird. So if I multiplied this by 9, if I took 12.5, multiplied it by 9, then I would get the new area. Well, what's the relationship between this 9 and the scale factor of 3? Well, 9 is the squared version of 3. Does that have anything to do with it? And you know what? It does. All right. Now, here's why this is going to work the way it is. And I'll explain a little bit more, and we'll kind of wrap things up here. But if I go back and look at how I originally did the 112.5 area, okay, so let me clear this off. Let me clear off the perimeter here. So how did I get that 112.5? I took 1/2 base times height, and the base and the height were both 15s. Oh, so the original base was 5, and the new base was 15. Well, how many times bigger has my base gotten? The base has gotten 3 times longer. What about my heights? The original height, nope, different color, please. The original height was 5, the new height is 15. How many times bigger, or longer I should say, how many times longer is the new height? It's 3 times bigger. Oh, so the base got 3 times longer, and the height got 3 times taller. What's going to happen when I multiply 3 and 3? I get that 9 times difference. So there is a connection. I can still use the 3, but I have to adjust it ever so slightly to accommodate area. Remember what the units are for area. They are squared units, right? Inches squared, centimeters squared, feet squared. So what are you going to do with the scale factor in order to figure out the new area is you're going to multiply your original area by the scale factor squared, just like the units are squared. So here's my final let's pull it all together here. So what we found out was the dilated images perimeter, right? That was triangle A prime, B prime, C prime, is equal to the pre-images perimeter just multiplied by the scale factor. Now, perimeter is one-dimensional. And you might go, no, perimeter is all the way around a figure, and a figure is two-dimensional. Yeah, but perimeter is length, and we just happen to bend that length to go into different directions. All right? But perimeter is truly a one-dimensional thing. It's just length. So that's why we just multiply it by the scale factor. Now, in terms of area, the dilated images area, that was that 112.5, is equal to the pre-images area, that was the 12.5, multiplied by the scale factor squared. Now again, why are we squaring the scale factor? Because remember, area is a two-dimensional thing. It's based on length and width. So if you think about area as being two-dimensional, then that will tell you really what exponent that you need to have for your scale factor to multiply by. All right, so that's the new main idea here. All right, so you can use your old perimeter and your old area, but they don't get multiplied by exactly the same number. Perimeter, scale factor, you can multiply it. But area, multiply the old area by the scale factor squared to get your new area. Now we're going to talk about one more new concept here. All right? And the new concept is this: negative scale factors. What? Negative scale factors. We haven't talked about negative scale factors, but I have alluded in class that it's going to do something that we have talked about before. All right? So it's nothing new. You just haven't got to see it in play yet. So, given triangle ABC, determine the location of triangle A prime, B prime, C prime as a result of a dilation with a scale factor of negative 1/2 with a center at the origin. So we don't have to do any pretending here. And I just want to know, where's the dilation going to end up at? I'm not doing anything tricky. I'm not doing perimeter. I'm not doing area. Like, take a deep breath. We're just going to figure out where the dilation is going to be at. Now, you might be wondering, how are we going to tackle a negative scale factor? Just like we did if it was a positive 1/2. All right? So you'll see what's going to happen here. Something a little bit different, little twist to it. So A is at 1, 2, 3. So negative 4, comma 2. B, well, let's see. Let's go ahead and do it. Let's go ahead and multiply by the scale factor. So even if the scale factor is negative, we still multiply with the negative. So negative 4 times negative 1/2 is now positive 2. 2 times negative 1/2 is now negative 1. So I'm going to leave that for now. I'll come back and I'll graph it later. B is at 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. So 6 comma 8. Multiply it by a negative 1/2 scale factor. And B prime is going to end up at negative 3 comma negative 4. All right, one more time. C. C is at 1, 2, comma 1, 2, 3, 4, 5, 6, 7. So 2 comma negative 7. We multiply both of those by a negative 1/2 scale factor. And C prime is going to be at negative 1 comma positive 3.5, 3.5. All right, so now let's graph these. And really, that's the main thing I want to know, is just where's it at? All right, so 2 comma negative 1. There's A prime. B prime's at negative 3, negative 4. Okay, there's B prime. There's A prime. C prime, I forgot my end parenthesis, is at negative 1, 1, 2, 3.5. There's C prime. All right. So once I connect these, I mean, really, I'm done with the problem. I figured out where it's at. And now multiplying by a negative scale factor is something different, right? But I want you to look at A prime, B prime, C prime's triangle. It doesn't really look like it's in the same position, right, as triangle ABC. It looks like something has happened to it. Right? It looks like some other kind of transformation has occurred. It did get smaller, right? We can tell that the 1/2 worked. It did its magic. But what did the negative do? The negative did something to it, right? Because typically, we would see, like a smaller triangle that also, that's a terrible example. Let's try that again. We might see a smaller triangle that looked more like this, that still looked like this, but maybe a smaller version of it. And this A prime, B prime, C prime really doesn't look like a smaller version in the same position. So what happened here? And some of you might go, I don't know, did it rotate? Did it reflect? It definitely did something, right? And so here's where I want you just to kind of look at. Let's look at A, and here's A prime, and here's the center. And here's B, B prime, and the center. And C, C prime, and the center. Notice that the image coordinates, A prime, B prime, and C prime, are always exactly on the opposite side of the center. And if you have something on the opposite side of the center, think about what type of angle that's really creating. It's making a 180-degree angle, right? So did we really just take triangle ABC, shrink it by a factor of 1/2, and then spin it around 180 degrees, and now it looks like this? And yeah, that's what happened. So here's what you need to really understand about negative scale factors. We'll come back to that here in a second. Is you need to treat a negative scale factor. Really, you can just do it the way that you would normally do it. But the negative scale factor has two effects. The actual numerical part will do the growing or shrinking, like what we've seen previously. But really, the only thing the negative of the negative scale factor accomplishes is it really just rotates 180 degrees our points. And so now you might wonder, why does it rotate at 180 degrees? And so I'll answer that question here in a second. So I want to look at the next part here. It says, what effect would a dilation with a scale factor of -1 have? A scale factor of -1. And so what would happen if our scale factor was just +1? What if we multiplied everything by 1? Would anything change? And nothing would really change, right? And so just having a scale factor of 1, if k equaled 1, I would really say, in the end, nothing changes. But if now I have a scale factor of -1, what's going to happen? Well, again, this is where we got to break it into two parts now. The 1 is basically saying nothing changes. But what did we discover that negative did in our last problem? It rotated it 180 degrees. So if you had a scale factor of -1, that's the same as doing a 180 degree rotation. Okay? Now, here's where I want to prove to you that it's truly a 180 rotation and nothing else funny going on. So imagine, we have points here, right? We had A, we had B, we had C. We actually had numbers to go with those. But let's imagine I just have some point. Let's say I have point D, for instance. And I just call point D x comma y. And I go, hey, here's what I want you to do. I want you to dilate point D with a scale factor of -1. All right? So that means I need to multiply my x and y coordinates by -1. So D prime would end up at, so x times -1, that's -x. Y times -1, well, that's -y. Okay, so there's where D prime would be located, right? But now, maybe some of you are starting to see what's going to happen here. If I start at xy and I end up at -x, -y, notice I just switched the signs on my x and y coordinates, right? Positions didn't switch. What was that the rule for? Light bulbs. I could see them. Oh my gosh, this room is getting so bright. That's a 180 rotation rule. So in the end, when you see a negative scale factor, that negative says, hey, rotate it 180 degrees, and then when you have your number, you treat that number like it's going to get bigger or smaller. All right, last problem. It says quadrilateral ABCD. Don't have a picture, don't care. Could it be a square? Maybe. Could it be a rhombus? Maybe. Could it be a crazy quadrilateral? Sure. Doesn't matter. It's got a perimeter of 54 feet, though. So all four sides add up to 54 feet. And it's got an area of 72 feet squared. If ABCD is dilated with an unknown center, oh my gosh, getting crazy, unknown center, and a scale factor of -2.6, then determine the perimeter and the area of A prime, B prime, C prime, D prime. So basically, it's like this problem, but without the picture. All I know is what the area and the perimeter are. Okay? So let's start with our perimeter, right? The original perimeter of ABCD is 54 feet. And what did we say we could do with our scale factor with perimeter? So let's just kind of go back. Let me re-jog your memory here. What we found out was that if we took our original perimeter and we multiplied it by the scale factor, we got our new perimeter, right? But there's a little twist in this last problem. Because if I take 54 and I multiply it by the scale factor of -2.6, and then I've got perimeter of A prime, B prime, C prime, D prime, let's see, what does that come out to be? 54 times 2.6 negative equals, okay, so the perimeter is no, hold on, time out, negative 140.4 feet. And I would say, are you crazy? And the reason why I'm saying are you crazy is Can the length around a quadrilateral be negative? No, you cannot have negative length. So then what do we do? Is it positive 140? Do you just drop the negative? And really, yeah, remember, you need to think about, what did a negative do to a dilation? What did a negative do? A negative just said, oh, well, you're just going to rotate the thing around 180 degrees. If I rotate a quadrilateral 180 degrees, does that change the length of any of the four sides? No. So in the end, this is where you kind of have to think about these problems. And you're just going to have to go, you know what? That negative, that's only going to rotate my quadrilateral 180 degrees. It's not going to do anything to the length. So in the end, it's not negative 140.4, it is positive 140.4. Again, you cannot have negative length. All right, so now let's talk about area. Area of ABCD is equal to 72 feet squared. Now, again, that negative is going to do nothing in terms of area, right? If I took quadrilateral ABCD and I rotated it 180 degrees, that's what the negative is really implying here, the area is not going to change, right? But now I do get to multiply by the scale factor. But you got to remember something else. We don't just multiply by the scale factor, right? We multiply by the scale factor squared to get our new area. So I don't multiply just by 2.6. I multiply by 2.6 squared. So now the new area of A prime, B prime, C prime, D prime. All right, calculator. Need your help one last time here. So 2.6, first I'm going to figure out what that is squared, just for this calculator. All right, so 2.6 squared is, really it's going to get multiplied by 6.76. So 6.76 times our old area of 72 gives us a new area of 486.72 feet squared. And there's your final answer. So this isn't going to be the last time you're going to see a negative scale factor in a problem. So just remember, a negative scale factor, all that does is rotate your object 180 degrees. It does nothing in terms of length and in terms of area. All right, and that is finally all for this challenge day.